we will begin looking at applications of the derivative, first by finding local maximums and local minimums. That is, where our function is the largest and where our function is the smallest. Let's remind ourselves of a few things we know about the derivative. Recall that we say a function y equals f of x is increasing if the derivative dy dx is positive. And we say that the function y equals f of x is decreasing if the derivative dy dx is negative. Lastly, if a function's derivative is 0, that is, it's not changing, then we say it is constant. As we move forward, it will be useful to keep in mind that a function is increasing when its derivative is positive, and it's decreasing when its derivative is negative. We can visualize this idea using the graphs of f of x and f prime of x. Our function f is depicted in the graph on the left. Notice that it starts out increasing, so its derivative starts out positive. Eventually, the function f begins to decrease. This is where the derivative is 0 and then becomes negative. Our function f continues decreasing with a negative derivative until it reaches the point where it starts increasing. Once our function f is increasing, its derivative is positive again. So what's the significance of the yellow and purple points in our graphs? Well, in the graph of f of x, the yellow point is a peak, or a local max, while in the graph of the derivative, the yellow point is where the derivative equals 0. On the other hand, the purple point is when our function f of x has a pit, or a local min. But on the graph of the derivative, it is when the derivative equals 0. These high and low points, which we will call local maxes and local mins, are what we want to understand. Notice that for both of them, the derivative is 0. Let's now give a formal definition. We say that f of x has a local minimum at x equals c if f of c is less than or equal to all other values of f of x near c. Term less than or equal to all other values of f of x means that f of c is the smallest, or a minimum. But the restriction that we are only talking near c is why we add the word local. Similarly, we say that f of x has a local maximum at x equals c if f of c is greater than or equal to all other values of f of x near c. Again here, we use the word local to mean that we have to be talking near c. And the term greater than or equal to all other values of f of x means that f of c is the biggest, or the maximum. And we saw that for both local maximum and local minimum, that the derivative f prime of x is 0. So we will find this definition useful as well. We say f of x has a critical point at x equals c if its derivative f prime of c equals 0. Notice that if we have either a local maximum or a local minimum, then the derivative will be 0, so we have a critical point. On the other hand, if we know x equals c is a critical point, is it a local maximum? Is it a local minimum? Might it be neither? How do we tell? Let's go back to our graph. In the case where f of x has a local maximum, then our function is increasing before our local maximum and decreasing after, which means that the derivative is positive on the left of our critical point and negative on the right. On the other hand, when f of x has a local min, then our function is decreasing before the critical point and increasing after the critical point, which means that the derivative is negative to the left of our critical point and positive on the right of our critical point. Let's summarize what we just found in what we will call the first derivative test. The first derivative test says that if f prime of c equals 0, that is, if x equals c is a critical point, then if f prime of x is positive for x less than c and negative for x bigger than c, then x equals c is a local max. In other words, if our function is increasing for values of x less than c and decreasing for values of x bigger than c, then at x equals c we have a local max. On the other hand, if f prime of x is negative for x less than c and f prime of x is positive for x bigger than c, then at x equals c we have a local min. That is, if our function is decreasing before c and increasing after c, then at c we have a local minimum. The first derivative test is useful, but we will find a more efficient way to test if a critical point is a local max or a local min. To do this, let's go back to the graphs. Last time we looked at these graphs, we commented on if the function was increasing or decreasing. Now let's look at concavity. At the local maximum, we have a critical point, that is f prime of x is 0. In addition, f of x is concave down at the local max. Whereas with the local minimum, again we have a critical point, the derivative is 0, but additionally here we have that our function is concave up. As we did before, let's consolidate the information we just found. We have that f of x has a local max when its derivative is 0 and it is concave down. Our function f of x has a local min when its derivative is 0 and it is concave up. But remember that we can quickly compute exactly where our function is concave down or concave up. Our function is concave down when the second derivative is negative. So we can rewrite the first line as f of x has a local max when its derivative is 0 and its second derivative is negative. The second line can be rewritten as f of x has a local min if its derivative is 0 and its second derivative is positive. This can be summed up in what we call the second derivative test. The second derivative test says that if f prime of c equals 0, that is, we have a critical point, Then x equals c is a local max when the second derivative, f double prime of c, is negative, and x equals c is a local min when the second derivative, f double prime of c, is positive. Notice that there is one other possibility. That is, what happens if the second derivative of c equals 0? In this case, we say that the test is inconclusive. This is because if the first derivative at c is 0 and the second derivative at c is 0, then we may have a local max, we may have a local min, or we may have neither. There's no way for this test to tell. So let's sum up what we just discovered about finding local maxes and local mins. The first derivative test tells us that for a critical point when f prime of c equals 0, then if the derivative is positive for x less than c and negative for x greater than c, then x equals c is a local max. And if f prime of x is negative for x less than c, with f prime of x positive for x bigger than c, then x equals c is a local min. The second derivative test tells us that if we have a critical point where f prime of c equals 0, then if the second derivative is negative, x equals c is a local max. If the second derivative is positive, x equals c is a local min. And if the second derivative is 0, then the test is inconclusive. It's worth pointing out that the second derivative test is easier to use, but it can sometimes fail, which is when we want to use the first derivative test. Let's now look at an example using what we just found. Let's find all the critical points of the function f of x equals x cubed plus 3x squared plus 24x minus 12 and classify them as a local max, local min, or neither. To do this, we'll start by finding the critical points. That is, we'll start by finding when the derivative equals 0. Computing the derivative of this function, we get 3x squared plus 6x minus 24. So we need to solve the equation 0 equals 3x squared plus 6x minus 24. We can either solve this using the quadratic formula or factoring. Either way we solve it, we get that x equals 2 and x equals negative 4 are the solutions to the equation. So the critical points of f of x are x equals 2 and x equals negative 4. So we're done with the first part. Now we need to classify them as local max, local min, or neither. To do this, we want to find the second derivative. Since we've already computed the first derivative, we need to compute its derivative to find the second derivative. We can find the derivative of 3x squared plus 6x minus 24 to be 6x plus 6. We can now use this to tell if our critical points are either local maxes or local mins. Evaluating f double prime at 2, we get 6 times 2 plus 6, which is 18, and what we care about this is that it is positive. Since the second derivative at 2 is positive, our function must be concave up, which means that x equals 2 is a local minimum. F double prime of negative 4 is 6 times negative 4 plus 6, which is negative 18. Most importantly, it is negative. So that means that our function is concave down, which translates to x equals negative 4 is a local maximum. So we found our two critical points, x equals 2 and x equals negative 4, then classified them using the second derivative test to find that x equals negative 2 is a local min and x equals negative 4 is a local max.